Hello everyone and welcome to my YouTube channel. My name is Dr. Vile and the purpose of this YouTube channel is all about getting you ready for your A-level chemistry exams. And this video is going to focus in on the basics and introduction to atomic structure. So it would also be very useful if you were doing GCSE chemistry as well. There's going to be nothing in this video that goes beyond really GCSE level. So when we think of the structure of the atom, I'm going to sort of jump straight in. There are three particles that we need to be aware of. We need to be aware of the protons, the electrons, and neutrons. So three particles that make up an atom. We need to know those names. We need to know a little bit about each of those particles as well. Firstly, we need to know where the particles are found within the atom. Now, right in the center of the atom is the nucleus. And in the nucleus, you find the protons and the neutrons. So we've got our nucleus right in the center of the atom. And that has the protons and the neutrons. And then we have the electrons orbiting the nucleus in shells. So sort of surrounding the nucleus. I'm going to draw a diagram on the next page that will sort of show this, make it a bit more visual. We need to know a little bit about the relative masses of these particles as well. So I'm going to give you what we call the relative mass. Now that basically just means how heavy one of these particles is when compared to one of the others. So all of the mass in the atom comes from the protons and the neutrons. So we could say that they have a relative mass of 1. And then the electrons, well, this is a little bit debatable. Some people would say they have 0 mass because they act as a wave. Some would say that they have a negligible mass, a really, really tiny mass because they act as particles. I'm not going to get in on the debate here. I'm just going to call it 0 and say that it's got a relative mass of 0, but feel free to argue with me on that one. It doesn't really matter for the purposes of what we're talking about. So all of the mass in the atom comes from the protons and the neutrons. And we also need to know the charges of these particles. So protons, P for positive. That's the way to remember that one. Protons positive, P for positive, and they've got you could say a charge of +1. Then the electrons are the negative particles. And they must have a charge of -1. And then neutrons are neutral. And they've effectively got a charge of 0. So for atoms, which are neutral, it is fair to say that the number of protons must equal the number of electrons. So for a neutral atom, the number of protons must equal the number of electrons. If the numbers of protons and electrons are not equal, then we create ions. And I'm not going to have time to go into that into this video. I'll have to go into that in a separate video. But when you have ions, then the number of protons are different to the number of electrons. And when we change the number of neutrons, we create what we call isotopes. And we're going to look at that later in this video. Let's have a look at trying to draw this visually. I'm going to take the example of lithium. Now, if you look lithium up on the periodic table, on a simplified periodic table, you'd see the numbers 3 and 7. Actually, you'll see 6.94 rather than 7, but I'm not going to get to that just yet. We're just going to assume it's 7 for now, and then we'll come back to that. And we need to know what this actually means. Well, the number at the bottom, the 3, is the number of protons. It's called the atomic number. And the number on the top is the number of protons and neutrons. And it's called the mass number. So we've got 7 here as the number of protons and neutrons, and 3 is the number of protons. Therefore, the difference must be the number of neutrons. So there must be 4 neutrons here. So how this actually looks is in the center of the atom, you're going to have 7 particles. Let's just draw them as little balls. 1, 2, 3, 4, 5, 6, 7. And then I'm going to shade 3 of them in red. And these are our protons. And then the ones in white are your 4 neutrons. And I'm just going to focus on, for now, how you've been taught how the electrons are arranged at GCSE. This is a huge simplification, and I'm going to do another video on the more advanced, the more accurate way of representing the electrons. But at GCSE, you would have been taught that the electrons orbit the atom in shells like this, circles. And because there's 3 electrons in total, 2 of them would go into the first shell and then 1 would go into the second shell. But that is a huge simplification, and as I say, I will cover that properly in a subsequent video. Okay, so this is roughly what your diagram would look like. You'd have your protons and your neutrons in the middle, in the nucleus, and then the electrons orbiting the nucleus in shells. This is not to scale. If you want to try and get a picture of the scale of this, imagine a football pitch and you've got a football on the centre circle right in the heart of the pitch. Well, the nucleus would be about the size of that football, roughly, compared to the rest of the pitch. So most of the atom is actually empty space, and all of the mass in the atom comes in the nucleus with the protons and the neutrons. So it's this top number here that gives you the mass of the particular atom. We call this the atomic mass number. Okay, that in mind, let's look at another example. Here you've got sodium, Na, and you've got 2 numbers here, 11 and 23. So what this means is that you must have 11 protons, because this is the atomic number here. The atomic number is 11, and because this is a sodium atom, you must have 11 electrons, and the difference between the 2 is 12, so there must be 12 neutrons. Now I'm not going to draw this out, but you'd have your nucleus in the middle. Actually, I may as well do a little sketch. There's your nucleus in the middle, and then you'd have 2 of your electrons in the first shell. That shell is now full. Then you'd move to your second shell, which can hold 8. I'm just focusing once again on the GCSE way of doing this for now. I will do a separate video, as I promised, on SPD configurations, which is the more accurate way of drawing the electrons. This has used up 10 electrons, so we need to go to another shell, and then you just have 1 electron there. So its electron configuration would be 2, 8, 1. So you've got 11 protons, 12 neutrons, and 11 electrons. If you have chlorine here, 17 and 35, now I've deliberately picked one of the isotopes of chlorine just to illustrate my point. You must have 17 protons because the atomic number is 17. 17 electrons because this is a chlorine atom and therefore it must be neutral. And the difference between 35 and 17 is 18, so there must be 18 neutrons. And in terms of its electronic configuration, you've got 17 electrons, so it'll be 2 in the first shell, then 8, then 7. Sticking with chlorine, when you look at chlorine on an A-level periodic table, you see two numbers, 17 and 35.5. Now, what you cannot assume is that you have 18.5 neutrons. That is wrong. Okay, there are not 18.5 neutrons, but actually what happens is that chlorine is made up of two versions of chlorine. One of these is chlorine 35, and the other one is chlorine 37. So we've got two versions of chlorine. They are both chlorine because the atomic number is 17, but can you see that the mass number is different? And therefore, chlorine 35 has 18 neutrons, whereas chlorine 37 has 20 neutrons. And you might still be wondering where this 35.5 comes from. Well, if I told you that of all the chlorine in the world, 75% of it was chlorine 35, and 25% of it is chlorine 37. So this number here, 35.5, is a weighted average of the percentage abundances. So let me show you how we actually do the calculation, and then you can apply this to any example. What you do is you take the mass of the isotope, which is 35, and you times it by its percentage, which is 75. And then you add that to 37, which is the next isotope, times its abundance, which is 25. And then because these are all in percentages, we have to divide by 100. And if you put that into your calculator to three significant figures, you end up with 35.5, which is your atomic mass. So when you see the numbers on your periodic table and they are not whole numbers, remember this is the weighted average of all the different isotopes. And as we saw here, isotopes are atoms of the same element that have different atomic masses. So they have different numbers of neutrons. This is a bit of a whirlwind tour, but let's look at another example. Here I've looked up some data for the element iron, Fe. And iron has four main isotopes, one of which weighs 54, then 56, 57, and 58. And I put the percentage abundances here. And what I'm going to show you is how we calculate the atomic mass of iron. So you take the 54 and you times it by the 5.8, which is the first isotope. I'd stick that in brackets. And then you add that to the next isotope, which is 56, times 91.8. Then you add that to the next isotope, which is 57, times 2.12. And then you add that to the next one, which is 58, times 0.28. And as previously, divide by 100, which is a sum of all the percentages. And when you stick that all into your calculator, you end up with 55.9 to three significant figures. Okay, so whenever you see the data on your periodic table, it is just the weighted average of all the different isotopes for the atoms. And remember, we're just dealing with atoms here. I'm not going to deal with ions in this video. That'll have to be in a separate video. And just one last thing to consider. We've looked at atoms and their atomic mass so far. Atoms stick together to form compounds and molecules. So to work out the molecular mass of a compound, all you have to do is add up all of the individual atomic masses of the atoms that make up the compound. So I'm going to be using the WJC datasheet for this, and I've given 4 examples here. HNO3, well, hydrogen is 1.01, nitrogen is 14, and then oxygen is 16, but we're timesing by 3. And that gives you an answer of 63.01. H2SO4, you've got 2 hydrogens, that's 2.02. Sulfur, which is 32.1. And then 4 oxygens, which is 64. And that gives you 98.12. Magnesium hydroxide, you've got 1 magnesium, which is 24.3. Then you've got oxygen in the brackets, but we're timesing it by 2. So that's 2 lots of oxygens, that's 2 lots of 16. And then also inside the brackets, we've got hydrogen, which is 1.01, but we're timesing it by 2. So that's 2.02. And that comes out as 58.32. I'm not rounding these, I'm just giving them as they are. And then lastly, sodium hydroxide, which is 23 from the sodium, 16 from the oxygen, and 1.01 from the hydrogen, gives you 40.01. I hope that video was helpful. It's just a sort of very brief introduction to atomic structure. There will definitely be a follow-up video on ions, and there will also be a follow-up video on SPD configurations for working out how the electrons are actually arranged around the nucleus. Anyway, I hope that was helpful. Please like, subscribe, share, and I'll see you next time.